Okay, C++ has somehow managed to create at least 7 different ways of writing code that looks like it does stuff at compile time. We have const, constexpr, consteval, constinit, inline, and on top of all of that, we have normal if statement, if constexpr, and since C++23, we even have if consteval. If you are coming from JavaScript, C# or Java, these can look like variations of the same feature. However, they are most certainly not. Hey, welcome back. If you're new here, I'm learning modern C++ for ultra low latency systems and quantitative finance. Today, we're gonna learn about keywords that I mentioned earlier and how they affect final execution of the program. Let's get started with const. If I write this code, it means that after size has been initialized, I cannot assign another value to it through this name. And that's it. getSize could read a file, it could query the operating system or the API. The value can be unknown until runtime and still be const. That is because the keyword const is a type system promise about mutations. It is not automatically a compile time promise. Basically, if your variable is marked as const, you're promising that you're not gonna change it after the first assignment. Now compare that with constexpr. When it comes to this keyword, we can use it in 2 different contexts. For example, if I write this code, the initializer, aka the code on the right side, must be a constant expression. This means that if the compiler cannot compilate it during compilation, the program does not compile. For variables, the constexpr keyword basically implies the previously mentioned constant value promise. However, constexpr functions, not variable, functions are more confusing. As an example, let's see a constexpr square function. If I call this function square with a value 4 as an argument and use the result as the size of the std array, the compiler has to evaluate it at compile time. However, if I read a number from standard input and pass it into the exact same function, it can normally run at the runtime. You see, a constexpr function does not mean it always runs during compilation. It means it is allowed to run during compilation when the arguments and the context make that possible. Just a side note, the compiler may actually optimize other calls too, but there is an optimization decision made by the compiler. Okay, you may be thinking to yourself, but what if we want to disable runtime calls to any functions that we desire completely? That is exactly what the consteval keyword is used for. By the way, I don't know whether it's pronounced consteval or consteval or like const evaluation. I don't know, whatever. A consteval function is a compile time function. So every call to it must produce a compile time constant. For example, imagine generating a protocol identifier from a string. A string literal is fine. However, text thread from a network socket would produce a compilation error because there is no runtime fallback for these kinds of functions. The easiest rule to remember is that constexpr offers compile time execution when it's possible, and consteval demands it. And then C++20 gave us constinit, which sounds nearly identical, but solves a totally different problem. Constinit is mainly used on variables with static or thread storage duration. This can include globals and thread local variables. Basically, it guarantees static initialization instead of dynamic initialization later. This helps avoid unsafe initialization order between global objects. One big caveat is that constinit does not make the variable constant. For example, this code I can write and it's totally valid for me to increment the request count and decrement it, or just do whatever with the variable. Only thing that this keyword, the constinit, guarantees is the initialization timing, but the value is still mutable. Okay, now that we have the const fiasco behind ourselves, we can talk about inline, because this might be the most misleading keyword in modern C++. Because from my experience, most developers and me when I started out, when we see inline, we think it removes the function call and passes the function body into the caller. What I mean by that is that basically it takes the function body and just copy and pastes it into the function instead of the function call. The thing is, modern compilers decide that independently of us. They can fully ignore inline on a massive function and instead inline a tiny function that does not have the keyword. That means that today inline is mainly a language and linker rule. It allows the same definition to appear in multiple translation units without violating the one definition rule. For example, you can see this if you define some function as inline in a header that is included across many source files, and it will not produce a duplicate symbol error. By the way, fun fact of the day, functions defined inside a class body are implicitly declared as inline. This also applies to constexpr and consteval functions. And now we reach the normal if statement versus the if constexpr statement. As we all know, a normal if statement chooses a branch to execute at the runtime, basically when the program runs. The optimizer may remove an impossible branch, but both branches still need to be correct to compile. If constexpr changes the compilation rules, its conditions must be known at compile time. And for example, inside a template, the branch that is not selected is discarded during the instantiation. This means that this is not merely just a faster if statement. It conditionally creates valid programs from templates. And it's not exactly just a preprocessor, because the discarded branch still needs valid syntax, and invalid code does not become legal just because it's for example, behind if constexpr false. And finally, when you think we're done, cplusplus 23 added if consteval or if consteval. This is used inside constexpr capable functions, so something like this, when we want one implementation during constant evaluation and another at runtime. So for example, the compile time path might use a simple algorithm. However, the runtime path, since it needs to be faster, might use some specific instructions like SIMD or an operating system API that cannot be ran during compilation. What's interesting about this is that if consteval has no condition in parentheses, it simply just asks whether the code is currently being evaluated as a constant expression or whether the code is running at runtime. Like just to be clear, the condition isn't there at runtime, but it's there during compilation, and if it's hit during compilation, then it runs. And yeah, that's it. This video could be a little bit harder to get through or remember all of the specific details. So if you wanna, you can just rewatch it or to skip to specific parts. If you need to remember something, I'll drop the timeline of these parts below. And if you want to see more modern C++ explained through like real performance examples, or if you follow the HTTP server that I'm writing from scratch in C++, yeah, hit subscribe, and I'll see you in the next one. Bye.